All right, let's dive right in. We're looking at a cosmic mystery today that is seriously shaking the foundations of physics. For decades, we've had this standard model of the universe we rely on. But lately, new evidence has been pouring in that, well, it just doesn't fit. We're seeing deep cracks in everything we thought we knew.
So, what if all these strange signals we're picking up from the deepest parts of space aren't separate problems? What if they're actually clues? Clues that are all pointing to a single, pretty radical new idea. In this explainer, we're going to follow that trail of evidence together, piece by piece.
For a long time now, our guide to the cosmos has been what's called the lambda cold dark matter model, or LambdaCDM for short. And honestly, it's been amazingly successful. But recent super high precision observations are starting to show some really deep cracks in this beautiful theory.
Okay, so at the very heart of this crisis is something called the Hubble tension, and it's a stark disagreement. On one side, you have data from the early universe. I'm talking its baby picture from the Planck satellite, which predicts how fast it should be expanding today. On the other side, you have direct measurements from telescopes looking at the universe right now. And the two numbers just don't match. And listen, this isn't some small rounding error. It's a major discrepancy that has only gotten more certain with more data.
And you guessed it, the plot thickens. The massive dark energy spectroscopic instrument, we call it DESI, just dropped some staggering new data. It found statistically significant evidence, we're talking 3.1 sigma, that dark energy, that mysterious force pushing the universe apart faster and faster, isn't constant. It seems to change over time. And that directly contradicts the lambda, or the constant, in our standard LambdaCDM model.
So here's the crucial point. It's not just one problem anymore. When you crunch DESI's data through the standard model, it spits out an impossible result, a negative mass for neutrinos, which just can't happen. At the same time, the new Euclid Space Telescope is seeing that galaxies and cosmic structures are clumping together less than LambdaCDM predicts. These are all these weird, seemingly disconnected clues that our current theory just has no answer for.
But what if these clues aren't disconnected? A bold new theory is here that claims to solve all of them at once. It's called dynamic vacuum field theory, or DVFT.
The central idea of DVFT is profound and, honestly, a little mind-bending. It proposes that what we think of as empty space isn't empty at all. The vacuum itself is a physical, dynamic field, and its properties are the actual source of everything from dark energy to the effects of dark matter. Now, the theory models this vacuum as a complex scalar field, and it has two key properties. The first one is its amplitude, which we represent with the Greek letter rho. You could just think of this as the fundamental energy density of space itself, all the raw potential energy that's locked into the vacuum. The second component is the phase, represented by theta. And this is where all the action is. The phase is the dynamic, evolving part of the field. It's the changing kinetic energy of this phase over cosmic history that DVFT proposes is driving all these strange phenomena we're now observing.
Okay, so we have a new suspect in our cosmic case. Now for the really exciting part. Let's see how this single idea of a dynamic vacuum field just elegantly explains away all those troubling clues we've been talking about.
And this is what's so brilliant about the theory's power. First up, that evolving dark energy signal from DSI, DVFT says, yeah, that's just the natural evolution of the vacuum field's kinetic energy. What about that unphysical negative neutrino mass? Well, DVFT actually derives a real positive neutrino mass directly from the field's interaction with particles. And the suppressed growth of cosmic structures that Euclid is seeing, the theory predicts the vacuum's coherence creates a kind of friction that slows down the clumping of matter, exactly matching what we see. It checks all the boxes.
But here it is. This is the theory's most revolutionary, most stunning claim. DVFT proposes that we don't need cold dark matter. The gravitational effects we've been attributing to some invisible particle are, in this model, just an emergent property of the vacuum itself. What does that mean? It means there are no missing particles to find. This is not a small tweak, folks. This is a potential paradigm shift in how we understand the very stuff our universe is made of.
So what makes this new theory so compelling to physicists isn't just that it solves these problems, it's how it solves them. It really all comes down to unification and elegance.
Think about the standard model, LCDM, like a toolkit. To explain the universe, we've had to add all these separate, disconnected tools, a cosmological constant for dark energy, some hypothetical particle for dark matter, and we have to plug in neutrino masses by hand. They all kind of work, but they don't seem related to each other at all.
DVFT comes along and proposes something much more profound. It suggests that dark energy, dark matter effects,
Even neutrino mass, they aren't separate puzzles. They are all, and I'm quoting here, emergent properties of a single underlying physical entity, the dynamic vacuum. It's one elegant mechanism that could explain 3 of our biggest cosmic mysteries.
Now look, this is a beautiful idea, right? But science demands proof. And the great thing about DVFT is that it's not just some cool philosophy. It's a testable scientific theory that makes concrete, falsifiable predictions.
So how do we put it on trial? Well, the theory predicts several unique signatures we can go look for. First, it says we should see about 5% more weak gravitational lensing than we expect. Second, a subtle change to our cosmic yardstick, the way we measure vast distances. And third, a slight boost in power on the largest scales of the cosmic microwave background. These are real measurable things we can check.
And here's the best part. The verdict is coming, and it's coming soon. The very instruments that can make these measurements are either collecting data right now or are just about to come online. We're expecting major data releases from Euclid and DESI, plus the new Simons Observatory, all within the next couple of years. The universe itself is about to tell us if we're on the right track.
Which leaves us with this final, absolutely fascinating thought. For centuries, we've looked out at the stars and galaxies to understand the cosmos. But what if the deepest secrets, the answers to our biggest questions, have been hiding right here, all around us, in the very fabric of what we've always just dismissed as nothing at all? We might be about to find out.